All right, I'm here with Chiara Marletto and Vlatko Vedral for a final roundtable discussion of open problems and future paths that constructive theory might take. And I should emphasize that much of what we'll talk about is necessarily speculation, unlike some of the other interviews. But anyway, Vlatko and Chiara, thank you very much for joining me.
Pleasure.
Yeah, pleasure.
Great. So let's start with something that's in physics proper. I want to talk about the boundary conditions of the universe. So this would be the initial conditions of the Big Bang, and also maybe the final conditions of the universe at the end of the universe, whatever that means. I understand constructive theory might have something to offer in this domain. So I wonder if you could explain how and why constructive theory might solve the problem of why the initial conditions are what they are, and maybe also the final state of the universe.
Yeah, I think well, as you said, this is very speculative, so it's something that we haven't really worked out yet. But I think there is an argument to be made as to why constructive theory could, in some sense, offer a new perspective on this problem of the supplementary conditions that you give on top of, say, the standard laws of motion, right? So in the first place, I think you have to consider that in the traditional way of doing physics, these supplementary conditions are usually set by cosmological models, and there are some theories around that kind of speculate about what these supplementary conditions could be. But the arguments for why there should be one condition rather than another are, let's say, controversial, and they are still very much debated. So that's why, let's say, it would be nice to have a different take, which could offer maybe yet another angle on this problem, which is basically open. And I think constructive theory takes a completely opposite approach to the laws. So in a sense, you have as fundamental things not these laws of motion and the supplementary conditions, but you have these statements about possible and impossible transformations on a subsystem of the universe. So it's not, even talking about the whole universe directly, but the statements are really always about substrates that can be transformed into one another or cannot be transformed into one another. And so the idea would be to create a set of constraints out of these principles in constructive theory that will then provide a set of conditions that could then constrain also these supplementary conditions. So in a way, the supplementary conditions should be an implication of these constraints, and they should be explained in terms of those constraints rather than the other way around, which is what happens now. So for instance, you could say, there is a principle that says, let's say, that it's possible to copy information from one substrate to another. What kind of implications does that have for the set of resources that have to be present in the universe, which of course takes us to what should have been, what you might call the initial state, and what should, what the final state should be. So I think that's the reason why one might expect a solution, or at least a suggestion of a different path to explaining the supplementary conditions through constructive theory.
Yes, I mean, if I can add to that, the fact that if you follow the conventional route, in the sense of trusting the current theories, so quantum physics and general relativity, both should apply, hopefully, also to the beginning and the end of the universe. Then experimentally, we have very, very little data on which to rely on. So if you follow this route of, I would like to give you the initial state of the universe as best as possible, and then evolve it according to the either equations of GR or quantum physics, or hopefully quantum gravity, if we have it one day, then we have almost nothing to rely on. The measurements that everyone focuses on, the CMB, the microwave background radiation, is possibly the only measurement we have. And we are using the fluctuations there to kind of constrain, as Chiara said, our initial conditions. But I think to me this seems really insufficient to do that. So this other approach where you're trying to give other principles which would constrain that looks to me promising at this stage, given that we actually don't have much else to go on. Yeah.
So beyond studying the boundary conditions of the universe, one of the other sort of more physics proper oriented programs of constructive theory is to express the object level theories, as they're called, like general relativity, quantum mechanics, in terms of possible and impossible tasks, rather than the dynamical equations of motions that they're currently typically expressed in. So I wonder, let's say that project succeeds. What problem exactly does that solve? And also, do you expect regularities to appear in this task-oriented framework that would not have at all been obvious otherwise?
Yes, I think it's nice the way you put the question, because I think it's important to emphasize the fact that if the constructive theory program is successful, one thing they will do is to extract some maybe deeper, more robust symmetries of these of the two laws that you mentioned. And so the exercise of expressing these laws in constructive theory should consist really in extracting the fundamental essence of the two in such a way that things that make these two theories currently apparently incompatible, which may be just due to certain formal features of the two theories, will be left behind. And all you're left with is then this set of deeper symmetries, which if the constructive theory approach works, should be compatible and should be mergeable into a new set of laws. So let's say one way of using this approach of constructive theory and its principles is really to take these two theories, extract out of them their more robust features that have nothing to do with the specific details of, let's say, the formalism that they are currently using in order to express their principles and so on, and then use this new reformulation to merge them into something new. And that already tells you somehow that by doing this translation program, what happens is that really you are not completely expressing each of these two theories. So the set of principles that underpin both theories will necessarily be more general than either of those. And that's one thing that I think it's important to bear in mind in terms of constructive theory, that if the constructive theory program is useful and successful, it will entail principles that are more general than either of those two theories that we have. And in a way, the dynamical trajectories or the dynamical laws that you then use in order to, say, make predictions will be somewhat approximative consequences of these principles that you can then derive through a certain procedure. So in a sense, the kind of usefulness of the principles as it, in this problem of merging the two laws comes in exactly because you are somewhat leaving some details of these laws behind, and you are focusing on some deeper structure, which could be, for example, information theoretic or thermodynamical or whatever. And then you're betting on that one as being the most fundamental one. And of course, it's a guess and it could be wrong, but let's say that's the kind of plan.
You can, given quantum theory, you can certainly say what's possible and what's not possible to do. And the same with GR. But I think if you go into the domain where both of them should be applied, but we don't really know how to do that in a coherent fashion, then I think what Chiara was saying is very important, that you're trying to distill set of principles that are true in both of these theories, and then you carry them forward, hoping that the new theory will also be underpinned by exactly these principles. And I think we've had examples in the history of physics of this kind of thinking. You know, Einstein is probably the most famous example who had to, you know, he was facing two extremely good theories, Newtonian classical mechanics and Maxwell's equations, and somehow he was looking into a domain where both of them should be applicable, and yet theory could not really explain the experimental results at the time. So he was kind of thinking, what do I take from Newton and what do I take from Maxwell forward, and what do I reject, as it were? And I think that's more or less the program of the constructor theory, is what are the principles that will survive, hopefully, the new revolution.
So moving beyond what has been traditionally considered in the realm of physics, constructor theory also seems to capture what's important about knowledge, namely that knowledge is information that causes itself to remain instantiated. So it's a kind of abstract constructor. But I wonder, beyond just the definition of knowledge, what problems would a constructor theory of knowledge solve that are either open problems in maybe epistemology or in other areas?
So I think this is a domain which is, you know, very much uncharted. So we're going even in more of an uncharted territory than the earlier questions. So I think one thing that seems to me very promising is this fact that, so I suppose if you look in biology and in neuroscience and also in this field of artificial intelligence, there are lots of proposed definitions for what is the, you know, the characteristic property of an entity that can think and produce, you know, various things like new theories of physics, new works of art, new poems, and so on. And these definitions are often regarded by the physics community with slight suspicion, in the sense that they often get labeled as being, say, highly subjective, not quantifiable, beyond, let's say, the domain of quantitative science, and so on. And the hope is that by rooting the notion of knowledge, which is key to all of these features of a mind, let's say, into a physical property, which is this objective capability of remaining kind of embodied in physical systems that certain pieces of information have, you are kind of demolishing this sort of set of criticisms against you know, the idea that the phenomenon of the mind could actually be part of science, and it could be described in a quantitative way by physics and other disciplines. And so I think one important set of conceptual tools that constructor theory can provide is really this realm of concepts that go around the notion of knowledge, because they make this notion objective. And so they somehow put also some of the current existing things that, you know, concepts that, let's say, from epistemology to neuroscience to biology are being used in order to describe what is conscious as what can be creative, I mean, depending on what kind of phenomenon you're interested in. So it takes all of these existing notions and roots them into a fundamental property of physical systems that is based on counterfactuals that are objective and so on. And this seems to me like an important step to take a completely scientific take on these things and finally find, let's say, a theory of knowledge, which can then power all sorts of other applications, to, you know, from AI to even, you know, improving on our take on epistemology and connecting it to physics. That's one thing that comes to mind.
Yes, I think it's all about this our kind of dual understanding, if you like, of the world, which is unsatisfactory. You know, there are the micro phenomena, and this actually exists in every discipline that we're talking about. There are the micro phenomena that we understand really well, and there are frequently the macro phenomena that we understand, but in a very different way to the micro phenomena. And the question then is, how do we connect these two understandings? And you know, in physics, for instance, when we go from the micro quantum laws to the macro classical laws, we have various techniques in which we do this. You know, there is statistical mechanics and all sorts of other methods. But I think the constructor theory is hopefully yet another technique that will allow us to bridge the gap, because I think the principles that Chiara is thinking of are meant to be scale independent. They are meant to apply to microscopic as well as macroscopic systems, which is very beautiful, because that would somehow almost suggest the gap is not even there. It's an artificial gap because of the way we are thinking about stuff, but actually maybe the gap is not there. And I think this is beautiful, because just imagine the power of that. You know, currently, for instance, you're thinking understanding the psychology of a human being is one thing, and people devote a lot of time to that. But understanding how a whole society behaves is a completely different discipline. How do I go from an individual human being and all of the, you know, wishes, desires, transactions of individual humans to the whole society? Can I do that? And a physicist frequently thinks like this, because a physicist would like to think of the way that we go from individual atoms into collection of atoms. And then we are thinking, couldn't we do something like that even at the bigger scale? And I think the constructive theory for me seems to offer a different approach to this question. And that's what excites me the most, I would say. Yes.
And I think there are scientific theories that are very powerful, that are about phenomena that kind of are sort of explained by these principles, which are not necessarily quantitative, but they're just qualitative. And an obvious example is the theory of natural selection. So that theory is based very, very strongly on principles of physics. One of them is the kind of set of principles of the theory of information, because that rules the way in which complexity can grow and you know, the various things that are at the basis of evolution by natural selection. But it's not a quantitative theory, so it's not going to say you're going to have like X number of elephants by this time in the universe if you start with these initial conditions. It doesn't work like that, and yet it's a very powerful explanation that you can kind of construct. And so the hope is that maybe with these principles, you know, both together with the principles that constructive theory provides and the set of conceptual tools that it provides about knowledge, for example, you could maybe construct an equivalent of this theory for the mind, and the you know, for example, overcome these issues that are still open since Turing's initial questions of what is it that makes something you know, a mind. So how do you distinguish a thing that's thinking from something that isn't really thinking, and stuff like that. But I think it's nice to have a handle on these things that doesn't necessarily have to be quantitative, but it's still, for example, it's qualitative, but it's still scientific, and it's kind of based on principles of physics.
Yes, I think this excites all physicists, really, this question of, we're kind of going in this direction of reductionism, but I think the constructive theory offers a different kind of reductionism to how you would typically think about it in physics. So, you know, for us, the question is always how much of chemistry is really just physics? And then going one level up, how much of biology is really just chemistry and therefore just physics? And I think that those are the big questions that we are asking. You know, once you apply these laws of physics to biology, is there anything that's left that only kind of belongs to biology and it's not part of physics? And I think constructive theory puts a different twist on this question, as Chiara was saying, because it moves you away from these initial conditions let's calculate the evolution and let's see whether we get 370 elephants at some point in the evolution. And I think this is a different kind of explanation. And now I wonder whether we could even go beyond, as you said, and go from, you know, biology to psychology. Can you even bridge that gap, really? And I think to me, this is hugely exciting. I mean, these are wide open questions, and I think, you know, they will probably define the next 50 years of science, really.
Bold statements. I love it. So we already touched on a little bit artificial general intelligence when we talked about constructor theory of knowledge and so forth. I want to follow up a little bit on biology while we're here in biological evolution. So Chiara, you had written a paper some years ago, and you basically showed, really it was one of the earlier applications of constructor theory to what's considered non-traditional physics, and you showed that biological evolution is possible, provided that the laws of physics allow for information carrying media. And I just wonder, do you foresee any future applications to open problems in biological evolution that constructor theory might either solve or help to solve?
Well, I think I think there are maybe two kind of relatively open questions that I think many people, both in the biology community, especially evolutionary biology community, and also in the physics community, let's say, find very interesting. So one question is that of is there an arrow of complexity? So, you know, we know that there is this well, some versions of the second law in thermodynamics say that there has to be some kind of irreversibility in certain phenomena that occur, for instance, in macroscopic heat engines, for example. And then you can maybe take some of these statements even in the micro domain by using some techniques of statistical mechanics and of non-equilibrium, for example, and so on. And these are laws are still about things that are inanimate and they don't contain necessarily living entities. But the question that is natural when you see, say, an ecosystem evolving is whether you could make a statement about a similar kind of irreversibility, a similar regularity about how knowledge in biological type of knowledge, so the knowledge in the genes, for example, is accreted and grows, let's say, with time. And of course, you have to be a bit careful because you don't want to end up saying that you know, boundless progress is necessary and will happen, which is kind of something that's in contrast with the idea of natural selection in the first place, in the sense that evolution works, but can get stuck, can go backwards, and so on. But the question is there a trend? Can you identify conditions under which, let's say, even maybe in some subsystem of the universe, you can identify some kind of arrow of complexity that indicates that complexity or something, which we may call complexity or knowledge or whatever, has to grow. And this is an open question. I think there are all sorts of studies currently being pursued. I think myself, I had a nice collaboration with Sarah Walker, who is an astrobiologist who is interested in these kind of questions. And again, constructor theory at this stage can't provide a theory for these things, but it can provide tools that allow you to talk about these entities in a kind of objective and physics-based way. And I think this is always important because it's a step kind of zero in order to then construct a theory that could maybe resemble what we currently call thermodynamics. So that's one, let's say one aspect of biology that could be sort of enhanced by tools of constructor theory. And the other aspect, of course, is maybe it doesn't quite fall into biology, strictly speaking, but there is this theory that von Neumann started, which is the theory of the universal constructor. Well, actually, he didn't provide the theory for that, but he, of course, suggested the whole idea of this machine that can be programmed to perform any task that's physically permitted. Mm-hmm. And of course, you could then bring this concept through the constructive theory approach that sort of takes that and sort of develops it further. You could take that set of concept into biology and see whether that is useful in order to understand better the way in which, for example, life originates, because the story of the origin of life is really a story of how you start with things that are not constructors and are not programmable, and you end up with things that are programmable constructors. And the kind of usual, I mean, there are also some models for the origin of life, but I wonder whether this notion of constructor and programmable constructors could actually help sharpen these models and make them better and make them more viable, and even maybe suggest a way of say, emulating or simulating this kind of origin of life phenomenon. Because currently I don't think we have, there is no computer program that can emulate faithfully this process on a computer under the conditions that are resembling the actual laws of physics. There are lots of computer programs that can simulate life, but somehow you have to help this to occur through various conditions that you put into the program itself, and so you're kind of cheating. So this is the second maybe application or kind of new take that constructive theory could bring to biology. So the idea of the theory of the universal constructor, which doesn't exist yet, but will exist hopefully if constructive theory works out.
Yes, I think this is again one of those phase transitions. We have some of these key times in the evolution of the universe that we're trying to understand. Of course, the origin of the of everything is the first big question there. And then, physics kind of takes you a long way. And I think it brings you to this origin of life then. And that's kind of the next big phase transition that we don't really know how to understand. How did inanimate matter become alive? It sounds like a very big, people talk frequently about consciousness, but consciousness is just the next problem. The first question really is why life, why did that even happen? And I think I completely agree with Chiara there that we do seem to need new kind of tools and methodology there. Yes. I think that currently science cannot really handle this properly and explain it in a satisfactory way. I mean, of course, we have various intuitions, we have various models, lots of them make sense, but I think we haven't quite grasped it to the degree that we would like to. And then this unifying feature, whether that phase transition could even represent a model for other phase transitions that we keep talking about. They could be negative, as you said as well, that evolution leads to greater complexity, but sometimes it diminishes complexity. So we know it goes backwards as well. There are major catastrophes there and so on. And I think all of this probably requires some unified framework.
Yeah. That we currently don't have.
We don't have it, yes.
Yes, it seems like many of these open problems definitely require a development of constructive theory further, which is very exciting. So beyond biology now, let's sort of take it a step further on the reductionistic hierarchy, as Vlatko had mentioned. I want to talk a little bit about free will. I know, Vlatko, you just mentioned consciousness. Free will seems like one of these ideas that if you take a reductionistic framework, then it's completely out of the question because everything, it turtles all the way down or whatever. But it seems like free will is enough of a regularity in the universe that it does require an explanation. So I wonder if you think constructive theory of knowledge and so forth might have something to say about under what conditions free will is possible, what free will even is in a physical understanding of reality and so on.
Yes, I think so there are, of course, this issue has been debated greatly, since the early days of civilization, in a sense. So, there are all sorts of philosophers in antiquity who were already kind of pondering what is it that makes us different, if at all, from other kinds of you know, animals, let's say, and from, say, inanimate matter and so on. So I mean, of course, constructive theory doesn't add to that yet anything, because we don't have a theory of that kind. But one thing that I find very you know, not so satisfactory, let's say, in the current way of tackling these questions, is that beside these philosophical debates, it's very hard, as you were saying, to even pin down what is it that we are talking about. So, you know, when we talk about this argument that was made at some point about the blind watchmaker, you know, you find a watch on the beach and then you say, oh, this looks very sophisticated and it's got the appearance of design. Surely there must be some entity that created this thing. Yes. If you ask the person that finds the watch, what is it that makes the watch so special? There is a sense in which you can at least articulate what's the functionality of the watch that appears to be, you know, wondrous and interesting. And it's basically the way in which all the cogs and the gears just kind of stick together to produce some sort of coordinated motion and so on. As you know, when you talk about consciousness or free will or any of these other, creativity, there are also terms around. We are not even, seems to me, at the stage where we can say precisely what is it that makes that. So we kind of, everyone finds it, you know, amazing when someone comes up with a new theory of physics, let's say, and that's an example of, great example of creativity being exerted, let's say. But what is the property of a brain that we are trying to explain? And so in that sense, I think the stuff that we are doing with constructive theory and this theory of knowledge could provide, let's say, the basic set of tools, the conceptual tools, to pin down what exactly it is that makes, you know, that we want to explain. So that's kind of step 0 to try to address the problem. And then, you know, you may find out that you, once you can formulate the problem properly, sometimes you notice that you can explain the problem away, in the sense that maybe there isn't a problem. And so all of these things are open, in a sense. And my current reservation is that it seems to me that we don't have the tools in order to create a kind of scientific theory of these things. But constructive theory may provide some conceptual tools. The other thing is that, of course, the theory of the universal constructor, again, which is something that I think David Deutsch is very interested in. I mean, currently he's kind of thinking a lot about this stuff, will necessarily touch on this issue of free will, because you see, a universal constructor, or being universal, does not, well, may or may not actually, but you know, it is our understanding that it doesn't have this feature of creating free thoughts, because it's a programmable machine, and it shouldn't actually be able to say, wait a minute, if you're programming me to do this, I'm not going to do it, and now I want to do something else.
Yes.
So even the theory of the universal constructor, the fully fledged theory, will probably fall short of talking about these entities that can create thoughts. And so, let's say, defining the theory of the universal constructor will help to explain what consciousness is, because we will have to make a distinction, scientific-based distinction, between what the universal constructor is and what, you could say, what David calls a universal explainer is. And I think, again, these are basically the very baby steps that you have to make in order to even construct a set of terminology that allows you to tackle the question.
Yes.
So it seems to me that that's where constructive theory at this stage can be useful.
Yes, I think it's even at the level of defining what free will would mean, because we are really even stuck there. As Logan said, we don't really know. Maybe even the name is inappropriate. In fact, it's not clear that this captures what it is that we are talking about in this case. I think as a scientist, again, you're thinking about experiments. You know, first let's define it properly, then let's test it. You know, and let's somehow try to show that maybe humans have more free will than let's say apes. which would maybe seem logical. But how does one do that? You know, what is your test that you really do have a considerable degree of free will? And as you said, you're trying to influence someone to do something, and you know that life is rebellious. Frequently, people will do the exact opposite to what you want them to do. But even this, of course, does not demonstrate free will, because, you know, this is your standard reverse psychology. If I know that you're going to do opposite to what I want you to do, I'm going to ask you to do the opposite, so you will do the right thing, as far as I'm concerned, if you know what I mean. So basically, you know, none of this really demonstrates anything resembling what we would like to call free will, I think. And yet somehow it's clear that more and more complex entities do have this feature, that they are, I don't know how to put it, I don't want to say independent of the laws of nature, because that's not quite true. We cannot afford to do that at all. Yes. But there is some feature.
Yes, some people say there's a degree of unpredictability in the train of thoughts, right?
That's it, something like actions.
That's right. So self-determination, something like that.
Yes.
So you see, the very fact that we are struggling to define the thing means that we are not quite there yet, even just conceptually at the philosophical level to talk about this stuff.
Yeah, but it definitely seems like, I find it interesting. A lot of times in the progress of science, the first step is honing in on the correct question. And it seems like, as Chiara, you were especially talking about, understanding that even a universal constructor doesn't seem like it would have free will. And so that contrast between entities that seem like they have free will versus the universal constructor, that seems like an interesting pathway that wouldn't have been obvious before constructor theory.
Yes, definitely.
So I think of economics really as a system of interacting people, or universal explainers, or entities that can create explanatory knowledge and so forth. Because constructor theory seems like it will maybe solve problems in areas like artificial general intelligence, theories of knowledge, and so forth, I wonder if either of you thinks that constructor theory will have anything to say about the regularities observed in economic systems.
Yes, maybe I can borrow some kind of comment that I think a friend of mine who's called Francesca Loria, who's an economist, made to me once. So she, you know, we were talking about constructive theory as you do. And I think, so Francesca was struck by the fact, and I think I agree with her, that especially let's say in macroeconomics, where there is a real struggle for using dynamical laws in order to make predictions about the market, or let's say, you know, large chunks of population making choices about what to buy next and so on. In those contexts, I think the techniques that mirror the traditional conception of physics, which are basically making predictions based on certain dynamical laws, these traditional tools don't quite work. And I think so. The comment was that there is a lot of need for principles, for let's say this approach that uses an explanatory framework that doesn't necessarily rely on the micro details of what's going on in the system, but it uses kind of statements about certain transformations, for example, being disallowed or forbidden in the same way the constructive theory does in, say, some of these principles I was mentioning earlier. And then shows, let's say, proves something like a no-go theorem about the impossibility of certain market configuration to be realized. And I think there are existing examples of this kind of logic already, but it's somewhat a minority view within the field. And the comment of my friend is that there would be a need for more of these explanatory frameworks in the context of macroeconomics, because another problem that they have, of course, is that it's very hard to perform experiments which would, say, confirm, unlike in physics, let's say a certain dynamical law.
Yes.
And so the fact of having more principles or constraints that are based on independently verified assumptions is even more kind of pressing than in physics, I would say. So I'm kind of thinking that this idea of scale independence and the fact that you can make these statements about the impossibility of performing transformations and then kind of following the same logic as you doing the constructive theory of information, for example, is a very promising set of techniques that actually might be useful in that field.
Yes, I think the only kind of you mentioned these no-go theorems, which is nice to know what are the configurations that cannot happen, for instance,
Yes.
given what we know. The only ones I'm aware of are simply due to the complexity of these systems. So, you know, if you, again, this goes back to these initial conditions, you know, if I tell you the current state and then I ask you to predict how many people will buy some shares, then actually frequently you can even link this to the halting problem. And you say this issue is so complex computationally that you cannot really solve this in general. But I think this is a very different kind of no-go to what you have in mind with the constructive theory, because again, it's to do with principles that should be satisfied independently of how many people we are talking about. And the transactions that they're engaged in. Again, as a physicist, this excites me a lot because I think people have thought a lot about analogies between economics and physics.
Yes, for example, the conservation of energy. Or...
Energy is an obvious one,
right.
yeah, that somehow, you know, it's quite, I think to a physicist, it gives you instantaneously a headache when you see how economists think about money, for instance, and how the whole concept is detached from anything physical. And, you know, people frequently say, oh, the price of something is simply equal to whatever someone else is willing to pay. But we know it's not quite like that because the resources are not infinite. It's not true that you can make whatever you like to make. And it's not true that someone else can pay whatever they like to pay. These things are constrained. And as you said, energy is an obvious one. You would imagine that a better economy is the one that more efficiently utilizes all the resources at its disposal. And I think it would be nice to have some kind of constructor-like principles that underpin this, and they could even explain macroeconomic features.
Yeah, and I think the fact that constructive theory offers a nice physical seeming definition of wealth, namely the set of all transformations an entity like a person or an economy is capable of causing.
Yes.
That definitely seems like a good result. So Chiara and Vlatko, thank you very much for your time. I appreciate this roundtable discussion. It's been a lot of fun and very informative. So I hope you have a good rest of your day.
Yeah.
Thanks a lot, Logan.
Thank you very much. It was great. Thank you.
Thank you.